Okay, so hi, Hagai Perets. Thanks for having me here. And actually, I worked on a lot of different aspects of free-floating planets, and I won't have time to talk about all of them. But I actually begin with apology because my past postdoc, Marish Bashkar, was supposed to give this talk. He couldn't come because of visa issues, and I discovered this morning that I'm supposed to give his talk. So I will do that, and he sent me a presentation, even changed the name already for the beginning. He actually did most of the work, but we worked on this together. So let's tell you, so many people discuss and study the scattering of planets, planet scattering, but far less studies have been done on what actually the properties of the ejected planets. And I think, so the previous review gave me great introduction and actually saved me a lot of time. But in principle, if you have closely packed planets in orbit, you can become unstable, actually go pretty fast about that. So if they're close enough, they become unstable, and then you start having planet scattering, and some of them can be ejected. As I said, I'm going fast because this was already explained. And one of the best ways to do that is using actually n-body simulations, because it could be pretty complex. Also, we actually have some nice analytic results, but today actually I'll focus on the more numerical results about that. So you put an n-body simulation, just put several planets, not too close to each other. We can actually play around also with how close they are and let them evolve in time just to do the gravity. Here we assume the disk is just dispersed and the planets are just encountering each other. And we can try to see what happens. And as shown before in the previous talk, we start having the planet scattering. You can see. Yeah. Okay. So we can see the evolution in all of the orbital elements until we can actually some them lose your planets, either through direct collisions between them, which then you don't lose the planet, but you may potentially form bigger ones, or they're just completely ejected. So let's try to focus a bit on what actually happens to these planets. So really, it depends, as I mentioned before, about the number of gas giant planetary systems. So generally, we are always left with typically 1 to usually 2 to 3 planets overall are left in the system, which means it doesn't matter how many planets or gas giant planets you started with, in the end, you're left with only these 2 or 3, which means that you have a large number of planets. They actually eject most of them. If you have only kind of 4 planets, you probably lose like 2 of them. If you have 10 planets, you lose something like 8 of them. So in principle, that's why you get these 30 to 80% ejected planets, depending on the number of systems, or number of giant planets that you have. And as you can see here, right, here you can see just as it evolves in time. And one of the interesting things we actually did, which most people have not done, is actually evolve it for a very long time, even up to 10 to the 9 years. Because usually when you think about planet scattering, you think the disk disperses, you start having this scattering, and like in 10 mega years, you lose most of your planets, or you get to a stable system. This is actually not exactly true. Yes, in 10 mega years, you get a lot of ejection, but you actually can get tetrahydrated even 10 to the 9. In some cases, at least in the case of large number of planets, you still evolve even 10 to the 9. So when we see systems and we think, okay, these are stable systems, they are old, this is not necessarily always true. You could actually have even still unstable systems, even when they are pretty old. You can also see here, this is just now in terms of fraction, right? This is just a count of how many number of planets are ejected. This is the fraction, and of course, as you get to larger number of planets, as I said, you can get to larger fraction, of course, getting lost through ejections. Okay, so one thing we learned already is we can actually have free-floating ejections even at very late time, and systems still evolve, if they have many planets at least, for a longer time than what people usually thought about the timescales, like 10 mega years or even 100 mega years. The other thing, this was actually shown in the previous talk, we also looked on the actual ejection velocities of free-floating planets. We now even have analytic estimates for this, but this was not in the original paper. But you can actually see this is a cumulative distribution of the velocities. And what you can see is that depending, of course, but typically you get kind of typical few kilometers per second. If you think about the potential, the escape velocity from young kind of stellar association clusters, these are in the regime of a few kilometers per second, which means that at least in the higher regime, you can actually lose the planets, even though they are not kept in the cluster. They're buzzing through, and then are lost to the field, and you have free-floating planets in the field, but not necessarily in the clusters where we many times see them, at least in imaging. The velocity actually depends on the energy that you have in the system. the innermost planet has the most energy in terms of potential energy, which means that if you have the innermost planet closer to the star, in principle, you can have more energy in the end to eject, and also they gave a kinetic energy, get higher velocities. And you can see here as with the 1 AU case, you get a larger fraction at the higher velocity compared to the 10 AU scale of the initial separation. So even the velocity distribution of free-flowing planets already tell us something about the structure of the planetary system which made them. So it's really interesting if we could actually ever get this distribution of that would be pretty cool. And of course, we can in a sense learn of it even from looking on clusters. Look on clusters of different escape velocity and see what's the fraction of free-floating planets there. It already tells you about this kind of tail of higher ones and how many you lose. Of course, there are many complications and complex. Each cluster is a bit different, but in principle, that's something that can be done. What else can change the number of ejections? One of them is just even considering the radius of the planet. If you assume just a point mass versus actually more realistic cases, you have less or more. And that's just because of collisions. Once you have a finite size, you start having collisions. Collisions actually you just lose planets. You get more massive ones, but you lose planets, so it means that you also lose many of the ejected planets, and you can see them, and they're kind of related in the same regime. You have strong encounters, very close encounters in order to eject them, which means that collisions take a bit of your free-floating. What else? Many times when people do planet-planet scattering, they put some kind of outer boundary where if planet goes beyond this boundary, they assume they just lost. Why? Because otherwise they have to simulate it for a very, very long time. So we actually try to play with it and see what's the dependence of this kind of potentially arbitrary choice of doing a cutoff. Because in real life, there's no cutoff. Well, there is a tidal field of the galaxy, or sometimes the clusters of flybys, but in principle, there's no actual cutoff, okay? So you can see there is a bit of a dependence. You can see that if you should choose only 100 AU, you have many more kind of free-floating planets ejected, or kind of you get lost much faster. But as you go to larger separation, in a sense, you can think kind of a convergence test. That at about 10 to the 4 AU, it's fine. You actually get this more or less very similar result, even in the evolution in time, which means that basically many of those kind of 100 AU systems actually evolve differently if you account for this for the wider potential separation that you can still live in. You can also learn something else from that, which is the following. If you now look on this again. This is a different kind of this is a different time scale, right? And you can see the different separations of planets which are in the system. And with time, of course, okay, you start with all of them very close, and you start having this tail of wide orbits, because some of the planets are ejected to wide orbits, and many of them are lost, as we know, right? And you can see it. But the interesting thing is that you can, even at a very long time, okay, even 10 to the 8 years, you still have these widely separated planets can still exist there. Those that do survive should generally, now you look on the eccentricity distribution, again with this time, should actually have very high eccentricity, which makes sense because they're usually scattered from the inner point, so the pericenter should be related to that. But this also could be really interesting. Once we see wide orbit planets, if we could measure the eccentricity, which is tough, of course, then in principle, if they are doing this process, they should have this high eccentricity in the evolution. And the other thing, as I said, is that we're discussing whether the free-floating planets in microlensing are free-floating or actually bound. Turns out you actually can get these wide orbits even after a long time in the system. Also true for direct imaging, where you look actually on young clusters or the short time scale, you can still see effectively unstable systems. They are wide orbit. They're going to be ejected, but it's still there. This was shown before, again, from our work. We can see the distribution of mass. This is for bound planets, and this is for ejected ones. As you can see, the lower mass ones are ejected, while the bound ones are more massive ones. Originally, the combination was more or less log uniform. So in a sense, they kind of separate. You have two different, you have complementary aspect between the free-floating and the bound ones, which actually is critical. So we think about free-floating planets. If we really want to understand planetary systems, even the mass function of planetary systems, we have to actually look on both of these things, because only the combined mass function is the real mass function of the planetary system. If any kind of Monte Carlo population synthesis try to produce a final correct mass function, they need to account for all of these things together. Okay, so people discussed before, told us a bit about how many gas giants we actually need in order to eject enough free-floating planets to explain what we see. So I won't go through this because it's more or less the same. I'm just going back to the same plot that he showed. He showed that you need about, this is from Sean Raymond's work, that he showed that you need about 10 kind of gas giants in order to get the free floating fraction that we have, which is a huge number, okay? Doesn't make sense that we have so many of them, which kind of seems like it excludes this kind of potential formation channel. Well, this is not exactly the case because, first of all, we have just new observations. So the number of free floating planets is actually smaller than what was thought at the time. And that's one thing. The other thing that previous simulation that studied this did not actually follow all the very long term, 10 to the 8, 10 to the 9 years, which you actually have give more ejection than if you cut it off earlier. So if you actually account for all this together, what you get is actually much nicer and prettier picture. In order to explain them, it's enough to get 4 or 5 gas giants. Still a lot, but not that big. In the solar system, which is a relatively stable system, right? We already have 2 gas giants and 2 ice giants, which are not that far away. So in principle, that might make it much closer. And even these numbers are assuming all these free-floating planets that people find in microlensing, all of them are actual free-floating planets, and it depends on the mass range, etc. So this probably should go down. So in principle, we probably go to 3 or even 2 gas giants, which start actually making the whole free-floating observation make sense and be consistent with planet scattering. So what was true 10 years ago, I think, might not be true now, and we actually might be in a good place in the sense that planet scattering can potentially explain this. And of course, we have many more constraints. You can look, as I said, the mass function, which will be different between the bound and unbound, etc. So if I try to summarize what we had here, so we said that we have the planet scattering can actually eject a lot of the planets, even up to 80% if you're talking about large system of 10 planets, and of course smaller one if you're talking about smaller numbers. They can actually potentially explain the observed free-floating planets. Not necessarily yet the properties, because we don't have a good understanding of all that, but actually you can try today to combine all the constraints that we have from the mass functions, the number, what we see is the bound planets and the non-bound planets, combine all together, and I think the constraints are actually pretty strong today, that if we combine all of them together, we can kind of really say and really reject some of these models, or really say that we have a good explanation for all of this, or we actually need another source of free-floating planets, for example, like brown dwarf-like formation or star-like formation. So I think the situation is a bit nicer than we might have thought if you actually consider the more detailed simulations and the current observation. And with that, I'll finish. Thank you very much.
Thank you, Hagai. Any quick question or two? Sure, David.
That's a really interesting conclusion, Hagai, about the 4 giant planets in each system. So I thought that the occurrence rate of Jupiter analogs found from the exoplanet side of things using radial velocities was much lower than that, around sort of 10%. So if there really are so few Jupiter-like exoplanets in these sun-like stars, how does that comport with this thesis?
Okay, so I'm not sure about the current census, but in principle, the census that we had at the time was between 0.14 and 0.5 have at least 1 gas giant. This is actually in a sense of accounting for that. It means it says that what's the fraction of system you need to have with 4 planets to get there. So it's not that you need all of them together, okay? You need just some reasonable fraction for them in order to get there. So, but I'm not sure whether consensus is very different from these 2 lines between 0.14 and I think 0.5 or so. It's just at 0.1, it's actually comparable to that in that sense.
So then if it's 0.1, you need more to make up for it? You need like 8 planets or something in those other systems? Or?
Yes.
Okay.
The less, of course, you have, the less of those, you actually need a larger number of other ones like this, which larger number. Of course, this is just assuming a specific number. In reality, you have a combination, so it is more complicated than that. You need to account for that. It doesn't account for ice giant, which also help, etc.
Okay, one more quick one, Will. Oh, are you good?
Basically the same.
Oh, same as David's question. Okay, let's thank Hagai one more time.
Thank you.